The second part of 5.1, we're going to talk about some applications of quadratic functions in real life contexts. And primarily, we're going to be talking about maximizing area or revenue in different situations. So the first thing is finding the maximum value of a quadratic. And so our first context is going to be working with this farmer wants to enclose a rectangular space for a new garden within her fenced backyard. So she's purchased 80 feet of wire to enclose 3 sides, not 4, and she'll use a section of her own backyard fence as her 4th side. So I'm just going to draw just a tiny sketch here so I can kind of get a handle on what's going on. So if that's what she's doing, then she's going to build her garden right here. Right, and so this will be length, width, length, and then we're not worried about this backside because this is her existing fence. And so what we're trying to do is maximize the garden size with the given 80 feet of wire fencing that we can use for these 3 sides. And so the first thing we'll need to do is we'll need to write a model that's going to relate that 80 feet that we have to these lengths and widths. So the first thing we'll do is we'll say, all right, well, I've got 80 feet, and that's going to equal whatever the length is, plus whatever the other length is, plus whatever the width is, right? And so combining those like terms, we'll actually have this expression, which will be 2L plus W, okay? And so then let's consider the formula it's asking for, and that is the formula for the area. And so the area of this rectangle garden is going to be length times width. Okay. And so we've got to figure out a way to relate the area of the fence to the specific parameter of 80 feet of fence. And so one of the ways we can do that is we can solve this expression up here for the width. So we can say 80 minus 2L equals W. And then we'll be able to actually plug that entire expression in to our area formula. And so that will be kind of how we'll tie those two together. And so I'll do that real quick. So we'll have area equals whatever this length is times the width, which we have defined as 80 minus 2 times the length. And so now we have an area formula just in terms of one of the variables instead of 2, which is the length. And so we can distribute that L, and we'll say, area as a function of the length. That's what we're working with. We input a length, and it's going to give us an area. And so we'll say L, well, let me write this in a way that you're more familiar with. So this will be 80L minus 2L squared. And so there's where your quadratic shows up. And this is a function or a formula for the area, relating it to the existing fence of length L. And so this is the function that's asking us for in part A. And then it asks us to apply that model and say, and this is the diagram. It's a little bit better to see, but we already saw it up here. So what dimension should she make her garden to maximize the area? Well, all we're really asking is what is the maximum of this function? What is the maximum of this function? And so let's rewrite it in the general form, and that's so we have descending exponent order. So that'd be negative 2L squared plus 80L. And so really all we need to find here is the vertex, because that's going to give us our max or min value. Being that this parabola opens down, we will actually have, a maximum instead of a minimum. So that's good. So finding the vertex, using your normal methods, negative b over 2a and whatnot, you'll find that the vertex here is going to end up being 20 comma 800. And I won't show that here because we got plenty of practice with that in the previous section. But looking at this function, the input is L and the output is area. So, and that's going to be exactly how we're going to use this. So this is the maximum area because that's at the maximum or the vertex. This is the max area. And this is the associated length that will give us that maximum area. Because different lengths will give us different areas inside of that shape. But if we find the vertex, we do have the maximum. So that would be a length of 20 feet. And so going back to our original kind of thing here, we would find the width by plugging back into that. So, what's the width? If we have 20 feet of length, so we'll go back and that's 80 total feet, 2 times the length of 20 plus W. And if we solve that, we'll see that the appropriate width for those lengths is going to be 40 feet. And so those are the dimensions that it asks for. Notice here it says what dimensions. And when it says dimensions, it does mean it wants the length and the width. So bottom line, you just find the vertex to find the max value. And then in this case, we had to go back and figure out what the width of the fence associated this length of 20 feet would be. That's maximizing area. So you kind of have to do two things, a little bit of review kind of stuck in there. You could also solve this by graphing the function. You can see here, I've just plugged that into Desmos, and then there is your maximum at 20 comma 800. So at a length of 20, we're going to get our maximum area, which would be 800. And so finding the maximum revenue is another application of quadratic functions. And revenue is just how much money a company is bringing in. And so you can see how that would be of interest. And some background information on the problem we're about to do. The price of an item usually affects the supply and demand. So basically, if the price goes up, the demand goes down because not as many people are willing to pay that higher price. And so in that context, in that idea, a newspaper currently has 84,000 subscribers, and they charge a quarterly subscription rate of $30. So they did some market research and they said, okay, well, if we raise the price to $32 for a quarterly subscription, they're going to lose 5,000 people. And so what we're asking is, what is the price that we should charge based on that relationship of price going up and losing customers? What should we charge to make the most money? And so the first thing we're going to need to do here is we need to recognize that in general, revenue is calculated by P times Q. And that's where P is the price of the subscription. Let me write that here, subscription price. And Q is for quantity, and that's for number of subscribers. And you could use any letters you wanted here. But these are the ones that I've chosen. So from there, first, we're going to write a linear function to relate P and Q, kind of like we did with the length and the amount of fence we had to begin with in that first example. So we want to write a linear function to relate the price P to the number of subscribers Q. And so how are we going to do that? Well, we're going to do that exactly the way we did it in the last chapter. We're going to make an input-output table with P's and Q's. So when the price is 30, it says that our number of subscribers is 84,000. It says when they bump that price up to 32, they lose 5,000 subscribers. So then that would be 79,000. That's 5,000 less. So if we calculate the slope here using your normal slope formula, you're going to see that the slope is negative 2,500. And so just putting that into, a standard linear equation, we'll see that the output Q, the number of subscribers, is equal to negative 2,500 times the price plus some intercept B that we don't know what that is yet, right? But we know from the last chapter how to solve that. We're just going to take either of these data points and plug it in and then solve for B. And so after you do that, it'd look like this. You'd take whichever of the points you wanted, plug that in, solve for B, and you'd end up with a B value of 159,000. And these numbers are large, but that's okay. And so that's going to give us our linear model. And so let's write that here. So the number of subscribers as a function of price is going to be equal to negative 2,500 times P plus 159,000, which is your intercept. So there's our linear function. Step one is done. Then we need to go back and recall that revenue, R, is equal to price times number of subscribers. And so we can take this expression for Q and plug it in here, and then we're going to have a quadratic again like we did earlier. So we're going to plug that in, P plus 159,000. Let's expand this and distribute that P so that we can actually see the quadratic we're looking at. This will be P squared plus 159,000 P. And so you'll see that this is a quadratic in the general form, right? That descending exponent order. And so, again, we want to maximize. So we're going to need to find the vertex because that's going to give us our max or min. Being that this parabola opens down according to our A value, it is in fact going to be a max right here. So that's going to be good. So finding the vertex, P comma Q, right, our H and our K, you'll calculate that using the normal, negative B over 2A, all that good stuff. You're going to find that this is 31.8, comma, and this is $2,528,100. Sorry, this should be an R, not a Q. I was wondering, I was like, what is that? So find the vertex, which will be P and R. That's what we're relating here. So this will be the price, and this will be the revenue, and specifically the max revenue. So this is the price that we need to maximize the revenue. So from there, let's go back and notice that the vertex of this is PR because these are P's and these are R's, right? The output is an R. And I'm sorry I put that Q there, but so there it is. So what is the max revenue? Well, $2,528,100, and that is achieved by setting the price of the subscription to this amount. Okay, so that is maximizing revenue, right? Then let's talk about X and Y intercepts briefly. We've already kind of seen this, we've done this. And so finding the X and Y intercepts, just as a reminder, a Y intercept is found by evaluating f of 0, which is basically just plugging in zeros for all the X's. And X intercepts are found by setting f of X, or the function, equal to 0 and solving for X. And you can do that by factoring, quadratic formula, whatever you want to do there. So let's first calculate the Y intercept. Which is calculated with f of 0. So that'd be 3 times 0 squared plus 5 times 0 minus 2. And that's just going to end up being 2. So the Y intercept is going to be X is 0, Y is 2. And so for the X intercept, we will, hold on. Okay, sorry. All right, so for the X-intercepts, we're going to just set the entire function equal to 0. And of course, again, I don't care how you solve this. If you like quadratic formula, do that. If you like to factor, do that. So either way you want to do that is fine. I'm going to factor it, and I'm going to say, A times C is going to be -6, and B is going to be 5. So I need two factors that sum to 5, and so that'll be -1 and 6. And so, just a reminder on how to factor something. So we can factor by grouping by saying 3x squared minus 1x plus 6x minus 2. Take the GCF of the first two terms, that'll be 3x minus 1. GCF of the second two, that'll be 2, so that'll be 3x minus 1 again. And so your factors are 3x minus 1 and x plus 2. And so once you've factored it, you just set each individual factor equal to 0, and you'll obtain your x-intercepts, which will be x equals 1/3 and x equals -2. And so here are your y-intercepts, here are your x-intercepts. Again, you can use factoring, you can use quadratic formula, you'll get them either way. And so looking at the next example, if we cannot factor, and if you don't like quadratic formula, you can solve by rewriting into the standard form. And so the standard form of this function, using the normal methods, you would find that the standard form is 2x plus 1 squared minus 6. And so from here, again, we want to set that equal to 0. And then there's a new method of solution that we currently have that we can work on. So we'll add 6 to both sides, and we'll end up with 2x plus 1 squared. And then we'll divide by 2 on both sides, leaving x plus 1 squared. We can take the square root of both sides. That'll give us positive and -3, and then just x plus 1 over here. And then finally, we can subtract that 1, and that's going to give us our 2 x-intercepts. So it's a little bit easier sometimes than factoring. Hang on one second. All right, I'm so sorry. I had to do an interview for something. I don't know. So basically here, like we were saying, remember this actually does give you both intercepts, because one of them is the positive root and one of them is the negative root. So you end up with both of the x-intercept. And I mean, again, you would have gotten the same thing if you had used the quadratic formula. Maybe you just like this way better. I just need you to know that it's a possibility. And another thing is, I do not care if you give me this exact form or if you do this as a decimal. It doesn't really matter to me. And so finally, you give it a try. If you want to pause and see if you can find the x and y intercepts of this quadratic function shown here, and then come back and see how you did.
Teachers, please excuse the interruption. Any students who are interested in the swim team,
all right, so this will be no x-intercepts.
Swim team, 245. Thank you.
So that means you got a domain error or something whenever you tried to do the quadratic formula, or you just couldn't solve it anyway. And then the y-intercept in this case would be 0,13. So last thing are the applications of the y and x-intercept in a quadratic application problem. A lot of times these are about like balls or rocks or blah, blah, blah that's being thrown. But essentially here, what you need to figure out first is, you need to find the vertex of this function, because it's asking us about maximum height, when it occurs, etc. And so the vertex for this function, the x is going to be that t, which is time, because that's the input, and the output is going to be, that h, which is the time, was the height. And so this will be time, height, and I don't care what letters you use, as long as you know that the input is time and the output is height, you'll be fine. So calculating the vertex with all the stuff we've already learned, you'll find that that vertex occurs at 2.5 and 140, and that is a max. And so remember, this is time. So this is asking when the ball reaches its maximum height, and that is 2.5 seconds after it is thrown. And what is the maximum height? Well, that's the 140 feet. And when does the ball hit the ground? And you have to understand that when a ball hits the ground, that means that the height is 0. And that would give us, t comma 0, which would make this a t or x intercept, which is basically just an x-intercept, right? Like you don't even have to worry about all these crazy variables in your mind. You just need to understand that's the x-intercept. And we know how to find that. So you would do whatever solving method you wanted, set this function equal to 0, quadratic formula, factoring, the last method I showed you, whatever. And you would determine that you have two x-intercepts, one occurring at negative 0.458 and the other occurring at 5.458. And so, these are time, right? And so negative time definitely doesn't make sense. So we're going to take this one. So this would be 5.458 seconds after the ball is thrown. And so that's pretty standard. Find the vertex, find the intercept. So if you want to try this one, it's just another example. If you want to pause the video and come back and see how you did finding that. All right, so you would have found that this is 3 seconds. Max height is 256 feet. And it actually hits the ocean 7 seconds after it was thrown. So hopefully that is helpful to you. Go ahead and work on the rest of the problem set in 5.1, which are just those real world application kind of word problems. Give those a shot. We will have a short quiz over section 5.1, both this section and the previous, on Friday. So just a heads up on that. And I will talk to you guys tomorrow.